哎，今天在座应该都没有外籍学生嘛，哈，那我们用讲中文就好了，是不是？去年上课的时候，有学长，你们的学长就跟我讲，老师，上课讲中文好了，我们跟你保证啊，教学意见调查的时候，我们会都说你用英文上课。OK， 有一件事情哦，是这样子的哈，用英文教学这件事情好还是不好？我自己对这个政策当然不是绝对需要了。不过这个 is not relevant here。有一件事情是千真万确的哈，你们选这样子的 ，OK， 你们选 the fact that you chose to enter the course given in English。I think demonstrate that you are very courageous. Okay. After all, for most of us are Taiwanese students. Our mother language is Mandarin, and you choose to enter this English program. So this, I think, demonstrates you are a very courageous young man or young woman. Okay, and I respect that a lot. This statement comes from the bottom of my heart. All right. Every piece of that statement is true. Okay. All right. Now, today, in the beginning, okay, we will talk about different criteria for system classifications. The first possibility is that we can classify system into instantaneous system versus dynamic system. As we saw this picture before, okay, this is a gear train, all right? Assuming that there is no gear backlash, okay? Then this is a very good example of an instantaneous system because let's assume this is input and this is the output. When I say input output, I'm referring to the rotating speed of the gears, all right? Once you change the input of here, the output speed here will change accordingly and more importantly, instantaneously. There is no delay. So put this in perspective in the context of control. This means controlling an instantaneous system is actually very straightforward because any input you apply will directly, without any time delay, impact the output, okay? So shaping the output to the way you want becomes a very straightforward task. However, so the properties of instantaneous system is that first, it has zero time delay because output changes simultaneously with the input. Why? Second, and this is also a very important property, it is that it is memoryless. What do I mean? Memoryless. What is the concept of memory when it comes to control? 麻烦把音量关小声一点 all right? The output depends, okay, oh, thank you, very good. All right. 再小声一点点 all right. Okay, this is good. Okay, thank you very much. I'm very lucky to have a great TA to assist me in this course. And should you have any question regarding to this course, you can always go to him for help, okay? He is a very competent TA, very good in control, also very good in programming, okay? I actually back him to become a member of my lab, okay? Literally, I back him to become a member of my lab, okay? I'm not joking. The output depends only on the current input, not on the past input or states. because the output has no bearing with the past input. That means the system does not have any memory. If I have memory, then that means I can remember the past. I don't have any recollection of my past. That means I'm a person I'm a memoryless person, okay? An instantaneous system is so-called a memoryless system because past has no influence on its current state, all right? And so this is also an important property, okay? Unfortunately, just like human beings, people have memory. Our past, our history have everything to do what we are today, all right? Hopefully, we can get rid of the negative memories. It is not easy though, okay? Mathematical representation. This is also an important property you need to understand. Instantaneous systems are often described by algebraic equations rather than differential equations, all right? By contrast, dynamic systems are often represented by differential equations because different equations has derivative, first order derivative, second order derivative, and so forth. So a dynamic systems, by contrast, are systems with memory, okay? For example, we showed this picture before. Water heater is a very good example of a dynamic system, right? Now, a dynamic system is a system whose output depends not only on the current input, but also the past inputs and its own past states. So there are two factors, okay, that will change the state of the current input. That is past inputs as well as past states, okay? So what the system experienced before, okay, has everything to do what the system is today, okay? Now, the characteristics of dynamic system include, first, energy storage. This system typically store and release energy, leading to time-varying response, okay? That does not mean the system has to be time-varying, all right? We will talk about, because it only means its response, which is output, can change with time. The reason why its past has impact on the current input is because as a hardware or as a device, it can store energy, which means past input can transform into energy. And once it transform into the form of energy and store inside the system, then it can be released to influence the current state. So mathematical representation of dynamic systems, as I just said, they are often described by differential or difference equations, okay? Now, differential equations is for CT continuous system, and difference equation, as we will see very soon, is for discretized system or DT system, all right? Now, human body is actually a dynamic system. Why? For example, food intake as input and body weight as output, okay? Input is food intake, output is body weight. Apparently, in this perspective, human body is not an instantaneous system. If I eat something and our weight change instantaneously, then I probably will not become overweight because I see the consequence immediately. Unfortunately, consequence only occur afterwards. So I just keep eating and eating and eating, and then feel sorry later on, okay? Now, habit behavior. Body weight does not change instantly with food intake. There is a delay between eating and weight change. So this is because we can store energy, all right? Now, the body store excess energy as fat, okay? And memory effect, past food intake influence on current weight, apparently, all right? So human body it's not just about weight. There are many perspectives of human body operations demonstrate that our body, every one of us are dynamic systems. That is also a reason why controlling or maintaining the health, the behavior of our body is not an easy task. It's a dynamic process, all right? So once it becomes a dynamic process, instead of an instantaneous system, things become much difficult to deal with. From a mathematical point of view, that is because the mathematical model is now becoming more complex because we need to deal with differential equation instead of algebra equations. Okay. The next topic we want to talk about is time invariant versus time varying systems. Okay. Now, what is the definition of time invariant system? A time invariant system is a system whose properties do not change over time. Okay. The property of the system, input and output, are not property of the system. All right. Input comes in the system, then the system produces an output. The system as an entity is different from its input and its output. All right, like human body. Human body is input. Food intake, human body is the system. Food intake is the input. My weight is the output. Okay. Now, and the system whose property do not change over time. Okay. If the input to a time invariant system is delayed by a certain amount of time, the output will also be delayed by the same amount of time, but otherwise remain unchanged. All right. These figures demonstrate precisely that property of time invariance. Let's say Ft is the input, and Yt is the corresponding output. Okay. Now, the next thing I do is I apply the input to the system. The input is identical, but let me put it this way: the waveform of the input remain unchanged. The only difference is that I delay the application of the input by, let's say, t seconds. Okay, that's it. If the system is a time invariant system, the output will also delay by t seconds. And at the same time, the waveform of the output, the patterns of the output remains the same, remain identical. Okay, this is the property of time invariant system. Very important. Human body apparently is not a time invariant system. Why? If you eat the same amount of food at a different time, it will have different impacts on your body. Trust me. Science has already demonstrated that. Okay. Now, human body is. I'm sorry for the Chinese. Why did I miss it? Okay, human body apparently is a time varying system, right? Okay, now I want to show you this diagram again. Remember, a control system consists of 4 fundamental blocks: controller, actuator, process, sensor. Each of them has its own input and output. So here, actually, we have 4 subsystems. And in essence, each of these systems, subsystems, they are all dynamic systems. None of them are instantaneous systems, okay, in the real world, all right? Now, how do I describe a dynamic system in this course? A dynamic system is described by a differential equation And this is the formal specification of the differential equation that we will be used to model our dynamic system. All right? Here, the output, which is the solution of the differential equation, is y. Okay? And on the left-hand side of our differential equation, r represents the input. And the differential equation itself represents the system. So the process of solving a differential equation is actually given the system is known, given the input is known. By solving differential equations, we find the yt, find the output, okay? So this is the very goal of system analysis, okay? Now, we just talk about time-varying and time-invariant systems. If all the coefficients of this differential equation are constants, that means Q0, Q1, all the way up to Qn minus 1, as well as P0 all the way up to Pn minus 1. These coefficients, every coefficient of this ordinary differential equations, assuming they are all constants. If this is the case, then the system described or represented by this differential equation is a time-invariant system. Why? Because the property of this differential equation does not change with time, all right? The order are always the same, all right? The basic structure is always the same. All the parameters stay the same all the time. But remember, input and output can change with time, okay? It's the property of the system cannot change with time, okay? So when it comes to mathematics, the formal definition of time invariance, it depends on whether or not these coefficients are constants. Any of them, even just one, okay? One Q or one P, doesn't matter which Q or which P is a function of time, then the system is no longer a time invariant system, okay? Keep that in mind. All right. Next is also very important because it has everything to do with the practical implementation of control system methods. That is CT system versus discrete time systems. Typically, we need to convert, typically, the system we are dealing with, okay, the real system, the real physical system, typically are CT systems, okay? But often, we need to convert a CT system into a DT system representation. Why? Why replace CT with DT? We convert CT system to DT system for computer-based control task. Because nowadays, when we want to do any control operation, we use digital hardware such as PLC, such as microcontroller, such as personal computer, okay? Or whatever digital hardware you find useful, convenient, or handy. Now, digital computer work with discrete data at fixed time interval, okay? Now, no matter how fast our computers are, it only has finite memory. Its speed is also limited, okay? No matter how fast or how large the computers are, okay? So they cannot process continuous signal directly. Why? Because a continuous signal is a function of time. So its waveform is actually a curve. A curve actually consists of infinite numbers of points. At any time instant, I have a piece of information, okay? Now, how many pieces of information do I have? I have infinite numbers, infinite number of pieces of information, okay? Computer cannot deal with that. So, because computers have limited processing speed, and limited memory, okay? So we need to convert CT into DT. We will show you how to do that right away, okay? And the other reason we want to replace a CT system with its DT representation is that DT systems are easier to implement in software. Okay, writing programs for DT systems typically is much easier than writing program for CT system. Why? Because DT system can be represented by algebraic equations, and CT system typically as a dynamic, especially when dealing with dynamic systems, we have to deal with differential equations. Okay. Now, so and another reason is that it allows for simpler integration with digital sensors and actuators. Okay. Now, controllers, we use digital hardware as our controller. Similarly, for the remaining part of the feedback control systems, sensors can be digital, okay? Actuator can be digital, okay? If they are digital hardwares, then if my controller is also a digital hardware, then digital hardware talking to each other is much more straightforward, okay? All right. Now, how do we, the thing is, we understand the necessity of converting CT to DT systems, okay? So let me talk about more about how to perform such a conversion. A CT system is one in which signals are defined at every instant of time. If this is the case, we actually have infinite numbers of points we need to process. A DT system is one in which signals are defined as specific discrete points in time, okay? Specific discrete points in time, which means you have to first specify the locations of every DT system information, okay? You have to specify the locations. Now, usually in practice, these discrete points are equally spaced, which means the distance between the neighboring discrete time system sampling points is often a constant, all right? Now, CT signals must first be converted into digital form through a device we call ADC, all right? ADC is actually, what is the name of ADC? Analog to digital converter, all right? Okay. Now, ADC work in two stages, okay? Sampling and quantization, all right? What is sampling? Let's say this, green curve represent the signal of interest, the signal under consideration, okay? As you can see, it has infinite numbers of points. Sampling abbreviation means that I only sample these points as this preset at these pre-specified locations, all right? And as you can see, the sampling period is fixed, all right? And these sampling points are equally spaced. And this is the sampling period, okay? And 1 over t is the sampling frequency, okay? So this is a sampling operation, okay? What does sampling operation do? It converts a CT signal, continuous time signal, into a discrete time signal, all right? Now, let me show you a very, very simple example. Here, we consider a first-order differential equation, which apparently is a CT system, right? Because the output is X, input is U. Both input and output are functions of time, okay? Continuous function of time, where A and B we assume they are constant. So apparently, if this is the case, this is a time invariant system. Now, let's define our sampling period. Let's denote it as Ts, okay? And the sampled signals, that is the sampled values of the signal, is denoted as a Sk as well as Uk, all right? What is Sk? Very, very simple. It's just the value of X at the time instant of K times Ts, all right? Nk apparently is an integer, all right? It goes from 0, 1, 2, 3, all the way up, okay? Now, next, I can approximate the derivative by forward difference. Remember that there is more than one way to approximate the derivative, okay? This is only the very, very fundamental technique for performing such an approximation. There are much more sophisticated advanced technique to perform such an approximation. This is only as an example to show you how to go from CT to DT. This is by no means the only approach to do that, all right? Okay, let's just use this forward difference approximation to approximate our derivative, which appears here, all right? If I plug this into here, then this equation can be rewritten as this, okay? Remember that here, I need to replace X and U with this, right? This has to be replaced by this, and this U of T have to be replaced by U of K, all right? Now, here, let me rearrange this equation. Let me assume S of K plus 1 is the thing I need to determine. So we solve for K of X plus 1, which means everything is not related to X of K plus 1 should move to the right-hand side of this equation, all right? So we times the entire equation by T of X, all right? And then we move this to the right-hand side of the equality, and this is what we will get. Apparently, this is first of all, this is a difference equation. This is a difference equation, all right? Second of all, difference equation is an algebra equation, right? The next thing that you need to know that with such an algebra equation, determining the response of this system become very, very straightforward. Why? Because if you know X of 0 and you specify, and U of T, remember, U of T is the input. U of T is known. Why? Because you apply the input, right? Okay, in a domain of control, you determine the input. What you need to do is what will the output be, right? So to solve the differential equation, once you convert it into this discrete time format, solving X is very straightforward. The first thing you need to have is the initial values of X. And since U of K is known, then you know U of 0, you know U of 1, you know U of 2. Why? Because this is definition of U of K. If you know U of T, then you know U of K for every given value of K, all right? And then you just assume K equal to 0 and use this equation to determine X, the value of X of 1. Once this is available, then K increase to 1. And you can use this equation again to determine X of 2, right? And you just repeat this process again. So this is actually a recursive process, all right? And by repeating this recursive process, you can immediately determine the response or the solution of this differential equation, right? This is the reason why we told you that, where is it? Okay. One of the reasons why we replace CT representation with DT representation is it allows for simpler integration. I'm sorry. It is easier to implement in software, right? Because here, difference equation is really very straightforward to operate, right? You just use it recursively. And with nowadays the power, with the computational power of nowadays computer, solving such an algebraic equation is really no big deal. Actually, it's a piece of cake, all right? Okay, so here, remember that ADC, that is analog to digital computers, need to perform two operations. The first operation is sampling, okay? And sampling convert a CT signal into a digital signal. I'm sorry, discretized signal, okay? Discretized signal, okay? Why do we call it discretized? Because this point are discrete values of time, all right? Now, it also, the ADC also need to perform another operation, which is quantization. The idea of quantization is actually very similar to sampling, but sampling perform sampling operation on the time variable, okay? Quantization on the other hand perform similar operation on the values of the variable of interest, okay? This is what we call quantization. Once we perform such a quantization operation, let's say the blue line here is the original signal, and then the red line here becomes what we call signal after quantization, and we have a special name for such a signal. We call it digital signal, okay? What we are doing here is via quantization, we convert an analog signal into a digital signal, all right? Okay? So when an analog signal is sampled, we get values that are still continuous in amplitude, right? Okay? It just no longer continuous in time, but it is still continuous in amplitude. And that creates a problem, again, for the computer. Because computer cannot deal with the real numbers. Because real number might, such as 1.3, might have infinite numbers, infinite amount of numbers we need to memorize. Computers cannot deal with this. So at the end of the day, computer have to perform truncation, okay? Just get rid of, ignore the remaining numbers, okay? Quantization is the answer to such a problem, all right? So to represent these so-called continuous amplitudes on digital hardware, they must be mapped into finite set of labels. This process is what we call quantization, all right? Okay? Now, how do we perform such a mapping? Of course, the first thing is you have to divide the values into finite numbers levels. And as you can see, the distance between these levels, again, are usually equally spaced, are constants. These points these levels are equally spaced in amplitude, all right? Now, and the value, each sample value is rounded or sometimes truncated. What do I mean rounded? when, let's say, this number originally, I can only represent, let's say with my digital hardware, I can only represent real number as integers, okay, only integers. Then if I am dealing a number, let's say 2.6, running operation means I should replace 2.6 with 3, not 2, because 2.3 is closer to 3 than to 2, right? However, if the number is 2.4, apparently compared to 3, 2 is a near neighbor, right? So this time, I truncate 0.4. So in performing such a mapping process of quantization, I can either run the number or truncate the number, okay, to the nearest available quantization label, okay? And that creates some what we call runoff error. Runoff error enforces discreteness by mapping infinite possible amplitudes into finite set of representable numbers, okay? And this, of course, introduces quantization error, as you can see here in this figure. And the quantization errors can be demonstrated by the discrepancy between these two curves, okay? But so this, of course, is the problem, okay? Quantization assigns each sample analog value into discrete labels. Let me go back one step, okay? Now, simply convert a CT signal into a DT signal by performing sampling operations on the time variable, okay? Now, quantization operation convert an analog signal into a digital signal, right? So CT signal, digital, discretized signal, analog signal, digital signals, they are 4 different concepts. But nowadays, when we talk about digital signals, we often imply that the signal is digital as well as discrete time, all right? Nowadays, when we say digital signal, we mean signals are digital and discrete time at the same time, all right? Okay, but when it comes to the two definitions, CT signal are not the same as DT signals, all right? Because one comes from sampling, one is the result of sampling operation, and the other is the result of quantization, all right? Okay, let's say the number of these labels. Now, what is the number of these labels in quantization? It depends on the bit resolution of the ADC. ADC, again, represents analog to digital converter. For instance, an AP-ADC provides 2 to 8, which is 256 distinct labels. If you want to increase the resolution to decrease the quantization error, then you can increase the number of bits of the ADC, let's say from 8 to 12, and then it provides 2 to 12, which is 4,096 distinct labels, okay? Quantization error is something does not go away easily. This introduces randomness, random-like noise, okay? Because we have runoff error, okay? Now, so in dealing with digital systems, after performing quantizations, we want to minimize the impacts of quantization error. How do I reduce the quantization errors? There are 3 possible approaches. The first approach is a very, very straightforward. I just increase the number of bits in representing my real, to represent my original analog signal, all right? And that is, of course, possible, but there are 2 prices we need to pay. The first is, of course, the cost. You increase the number of bits, you also increase the amount of money you need to pay for the ADC converter, right? Very easy to see that. The second thing is that processing more bits require more computational power, right? So it's not just a matter of the cost of ADC, it's also increase the cost of your other digital hardware, such as microcontrollers or computer, the CPU of your computer, okay? Now, the other possibility is an oversampling. By sampling the analog signals at a higher than at a high frequency, and then averaging the result can reduce the effect of quantization error. Let's say my sampling frequency originally is 100 hertz, okay? And I increase it to 500 hertz. But what I really need is the sampling result of 100 hertz, which means I need the sample value of my output at t equal to 0, t equal to 0.01, t equal to 0.02. And that is good enough for me. Now, if I increase my sampling frequency, let's say from 100 to 500, what I can do is that, let's say, originally this is a signal at, let's say, exactly 1 second, okay? Then there is the next sampling points here and the next sampling point here. On its left-hand side, we also have 2 neighboring sample points. And what I will do is I will average the result of these 5 sampling points and to make it the result and replace the value of these sampling points with the average of these 5 sampling point results. Because sometimes quantization error, it can be wrong, it can be rounded or it can be truncated. When you round the number, you increase the amplitude of the signal. When you truncate the signal, you reduce the amplitude of the signal, all right? So one is a increase effect, the other is a minus effect, okay? And by using more sampling points and use the averaging results of those sampling points, you have a better chance to balance the positive and negative effects come from rounding and truncation, all right? Okay, and based on that very idea, we have the third method to reduce the quantization error, which is what we call dithering. What is dithering? It adds a small amount of random noise to the signal before quantization, okay? Why do we want to do that? Remember, usually in the field of control, we do not want noise. We want our energy, I'm sorry, our signals to be as clean as possible. Any noise is considered as a source of distortion. It will introduce inaccuracy. But here, why do we want to add noise on purpose? Okay. Now, because by adding a small, I emphasize a small amount of random noise to the signal before quantization, it can help to randomize the quantization error. Okay. Let me make this statement in more detail. Okay, explain this statement in more detail. In quantization, rounding or truncation, the quantization error is deterministic for a given input. If the input is fixed, then the quantization error is deterministic. That is, there is a chance 90% of time I'm doing rounding and only 10% of time I'm doing truncation. So in average, I will increase the value, increase the attribute, increase the value, increase the amplitude of the signal, okay? And that introduce bias into my digital signal, okay? Dithering randomizes the quantization process so that rounding or truncation decisions are no longer strongly tied to the exact signal natures, okay? So dithering makes the distribution of quantization outcomes, round up or round down, or truncate or not, more balanced and random, okay? Round up is a positive effect. It increases the amplitude. Round down or truncation is the negative effect. It decreases the value of the signal. And if the frequency of round up and round down are balanced, are equal, then the positive and negative effect cancel out each other. And that is what we want, because it will also lead to better spectral property. I will not talk about spectral property here because we still haven't covered the necessary groundwork for spectral analysis, okay? But I just want you to know, okay, this operation is good for time domain property as well as frequency domain property, okay? This is actually a very good technique, okay? Because it can reduce quantization error. And people tend to dismiss or ignore the quantization error, which is very unfortunate because it is there and it is always there. It is always possible that quantization error can be a problem for the inaccuracy of our control system. But people only ignore it. And that's for, as I said, it's very unfortunate. Okay, now let's move on to another possible classification criteria of our linear time invariance or our system, okay? A system can be distributed parameter system, or it can be a non-parameter system, okay? Now, what is, let's say this baseball bar, if I assume it as a rigid body, it is actually a non-parameter system because despite the fact a baseball bat have infinite numbers of particles, we always consider it as one single body, right? Okay, because we assume it as a rigid body. The relative position of those particles, those infinite number of particles of this baseball bat, remain unchanged. That's the very definition of a rigid body. A fishing rod, of course, is not a rigid body. It is what? It is a flexible. And this is the non-parameter system of this object into one body. And here is a distributed parameter system because every particle of that system can be considered as its own degree of freedom, okay? As you can see, this is much complicated to operate, okay? Now, let's first talk about non-parameter systems. Non-parameter systems can be adequately described by finite number of parameters that are functions of time. For example, for a baseball bat, what do we need to consider? Mass, moment of inertia, because each body can only perform translation and rotation. When it comes to translation, we have to consider mass. When it comes to rotation, we have to consider moment inertia. Finite, but at the end of the day, there are only two parameters we need to consider. Now, typically, spatial variations using systems are negligible, okay? Now, this system dynamics can be modeled using ordinary differential equation. We saw that again, and again. in the course of dynamics. Example including mechanical systems with rigid bodies. Okay, what are distributed parameter systems? This system involves spatial variation in their state variable. I forgot to give you the formal definition of state variables. Just remember that state variables represent a collection of variables that can fully represent the condition of the system. Okay, it's 10 o'clock. Let's take a 10 minutes break.